Hello everyone, welcome back. We can do more with other examples. Why don't we look at logical OR? It seems very similar to AND. How hard can it be? First thing is to pick our language, which usually just means to pick the symbols we want and the grammar. If we're using language, we would use words like either or. We could say either Jack or Jill, and then that would look like this middle disjunction. If we're doing programming, it's become common in many programming languages to use a vertical line and maybe several of them. But it's also not uncommon to type the words or in between. I'm going to use the mathematical notation of the upside down wedge, or the V. This is trying to hint at this close relationship between and or. I don't want to go too far with that because they do diverge pretty soon, in fact, but there is still a close relationship. So how do we introduce them? Well, it's actually the reverse of what we do with and. When we have A or B, P or Q, we need to just have one of them. And what that means is that we need to introduce them from either one. Either we have P, and that entails us to know about P or Q, or we have Q, and that entails us to know about P or Q. So there's two introduction rules. Remember and? It had two elimination rules, but only one introduction. Here we have two introduction rules, but maybe we'll have different number of eliminations. So how do we eliminate this symbol? Well, the first guess might be P or Q entails P. But wait a minute. Shouldn't P or Q entail Q? Or maybe it's neither one of them. Here's the big dilemma. It's unclear what we should get out if we start knowing P or Q. Is it P or is it Q? We have no idea. We know that one of them substantiated the claim, but we don't know which one. To solve this dilemma, we actually need a third-party vote. We need to know what would happen if P was true and what would happen if Q was true. So this is what is known as a disjunctive dilemma. So here we'll have a context, let's again fix gamma, and we'll have a proposition P that entails another one R. Now I don't know if P is true or false. I'm simply saying if I happen to have P, then it should lead to R. Likewise, if I happen to have Q, it should also lead to R. So notice what we're setting up. We're setting up two paths. Either P takes us to R or Q takes us to R. And I've said or because it's quite difficult to avoid and or in logic because they're so familiar to common speech that they're how we form some of the essential sentences to describe this logic. So now let's take it all together. I have a context, gamma. And that context, together with the assumption of P, would lead to R. And that context, together with the assumption of Q, would lead to R. Then, if I happen to know in this context that I have entailed P or Q, then what do I know? Well, the only way I could have entailed P or Q is if I started out knowing a P and knowing a Q, which means that the pending P and Q that are placeholders here and there, they're hoping to exist, they do exist once I know this side. Once I get past the turnstile, I have a conclusion. Since I've concluded P or Q, I now know there is at least one of these is true. Maybe it's P, and if it's P, I will get R. And maybe it's Q, and if it's Q, I will still get R. The conclusion now makes sense. If I have P or Q together with these two different paths, I will always get to R. This one's rather complicated, and it hints at some actual asymmetry between and or. We'll later get into sets and Venn diagrams, and we'll talk about De Morgan's laws, how we take complements and turn ands into ors. And it's misleading at first, because it's actually not true that these are just interchangeable concepts. One fits inside the other one, but not the other way around. The disjunctive dilemma pulls out the material difference between these. It's not as symmetric as you might have thought. How can we use this? Let's try to think of a sentence that uses an or. Probably any sentence you think of with an or will force you to do this. The key thing is, it's easy to introduce an or. You just need one thing to be true in the list. But this disjunctive dilemma is the one that takes practice. You will need to have the paths to a common conclusion from two separate places, a P place and a Q place. P place and a Q place have to both lead you to R in order to get the application. And we'll have some pictures when we get to categories to describe this. The key thing here is to just follow this example. Wet roads lead to car crashes. Inexperience leads to car crashes. Notice I've set myself up for a disjunctive dilemma. I have car crashes as my R, and I have two separate premises. One is wet roads and one is inexperience. So these are my P's and my Q's. Now I don't know if these conditions are satisfied until I get to the next part. Today there is a wet road or an inexperienced driver. I've just said this final P or Q. Now what can I conclude from this disjunctive dilemma? Unfortunately, it means we expect to see a car crash because R is the result under either one of these two paths. Both P and Q lead me to the conclusion of a car crash. So, in summary of these two, while enormously familiar and also interchangeable in many situations, and versus or are not perfect analogs or duplicates of each other, what mathematicians call a dual. It is true that and takes one introduction and two eliminations, and conversely, or takes two introductions and makes one elimination. However, what's not true is that they're perfectly symmetric. In the or, we need to use a much more complicated elimination formula because we don't know how to describe what got us into that stage. We could have gotten into it from two different paths. And so all we have to do is say when we were in one path, we could conclude the same thing as from the other path. That's how we'll use or. Let's try one more family of things. Let's just try to put truth on the table. What makes something logically true? How would we write that with the sequent calculus? Again, we're going to write down our three things. We're going to have a language, an introduction, and an elimination. The language seems pretty straightforward. We obviously wanted to have the word true, and let's throw in false as well. Now, the only subtlety here are some of the notations. Often it is the case that we use a capital letter T or the words little true or many other things in between. I'm going to prefer the one in green just to stick with one pattern. I'm also going to go ahead and call this term Boolean in honor of George Boole, who definitely spent a lot of time studying and proving what we knew about true. So in this model of logic, I'm introducing truth as just having two values, true or false. You can move into other forms of logic, such as fuzzy logic, where you might introduce intermediate values, somewhat true, very true, likely false, those kinds of things. But we'll stick with a two-valued true, false Boolean logic, whether you use it in words or symbols. Now, how would I introduce true? The key idea about truth is that you can just say something is true, but let me be careful what I mean by that. What I mean is I'm always allowed to conclude truth. It doesn't mean that I can say anything I want happens to be true. It just means that I can always end with something that is true. We say that by writing turnstile T. Another way to think about it is that you can put anything in front of this turnstile and it won't change the fact that true is true. This is what's known as a tautology, something that happens to be true because we say so, not because of any real reason. And you should think about this as not perhaps meaning anything more than just symbolically letting us get started with one fact. If we don't want true to be true, why would we call it true? So this statement is saying true is true. Now that we know that, what can we prove with it? Well, the key thing is to get information out of truth. And here, a subtlety emerges that helps us start to separate the ways that people see different logics. And this is the law of explosion. See, if we look at false, it's the tricky one. We know that not everything is going to be true. So we don't want to put true as something we can eliminate and guarantee some other outcome. In general, true doesn't imply something false. So we can't go from true over as a premise to some arbitrary conclusion. But false could perhaps be evidence for every conclusion. This is an assumption known as the law of explosion. The idea is that one false fact will explode and destroy all the logical claims you're making. And there's lots of reasons to think this might be the case. One of the reasons is simply that it helps us write down proofs of things. If we write a proof and we discover that x is both 7 and minus 7, we might think that can't be true. It has to be one or the other, but not both at the same time. And that complicated condition will make us explode into other contradictions and will eventually say nothing is true. So we use that to stop and say there must be a mistake in what we're doing. We can't have the situation of x equals both 7 and minus 7. Where is the mistake? So this law of explosion is a good way to know stop doing what you're doing and go fix something. However, in some types of logic, like paraconsistent logic, for example, if we're looking at a database, we can put information in which was true the moment we put it in, but the very next moment we look at it, it's already changed and it's been updated by some other transaction. So it never really was right exactly the way we said it. And so it's difficult to value truth and false as this type of explosion. Perhaps false should only allow explosion in some situations. That would be a paraconsistent logic. Again, we have to frame our opportunities and our goals, and that will help us know which rules to take in. So we're already struggling to do true and false? That's the point. The reason we need a sequent calculus is to articulate the subtle nuances we want when we're talking about logic. How do we want to reason with each other? It may not be what you think. And the sequent calculus separates our premises from our conclusions and tells us to write down very precisely the rules to go from one to the other. Without them, we're kind of just hoping everyone agrees with us, but we can't really prove it to one another. Let's try one more and then call it logical not. We've just created truth. How hard can it be to flip it to false? Well, De Morgan thought that was the rule. Boolean logic swaps true and false. But we've been more careful. We've used sequent calculus. We've introduced true from no premise, and we've eliminated false to any premise, to any conclusion. But we haven't made true and false completely interchangeable. And that is a key difference. It allows us to have nuanced logic, where not might not be what you think. Now, let's start out with our notation. There are lots of ways to write not. Perhaps the favorite is just the word not. It reads very well. But if you're in a symbol-based format, you might see a symbol like a little tilde or this little box here that we see. A common one in programming is the exclamation mark. It doesn't mean factorial for programs. It means not for some programming languages. Whatever notation you pick, stick with it. I'll stick with this green one. Now that I see this, I need to introduce a logical not. So the idea of a logical not is I have a premise and I want to get a new conclusion. So what kind of premise would be not? Well, let's think of the words. Premise P leads to falsity. That's a fancy way to talk about false. Falsity is the state of being false. So P entails falsity. Let's think what that could mean. When would you have some claim that you knew could prove something false? It would have to be a false claim. If you had something true that could prove something false, that would be a contradiction, an inconsistency. We wouldn't want that in our logic. So, if you ever discover that a premise entails false or falsity, you should conclude the premise is not logically true. So we would say the entailment moves to not P. The conclusion is no longer valid. This is how we prove false when we really need to be very specific. We find that the premise entails something false, and therefore we say, actually, not the premise is now true. That's a logical not. If you throw in the context, you get a slightly more specific rule. If context describes what it means to have premise, then entails falsity, then the context will entail not P. If P leads to falsity, it cannot be true. How would you eliminate this? How would you get rid of using a not? If you found a not P, well, you'd put a P in. Let's see that together. If we have a context that entails not P and a context that entails P, we get falsity. Now, why would you want to end with false? That seems very counterintuitive, especially if we're trying to do something like the law of explosion. There's the whole point. What we want not to do is to eliminate paths of reasoning. If we find something is not true, then ever bringing that close together with P means that we've blown up our whole logic into an explosion of false facts. So this is a good place to back off and say, don't go down that path. It leads to falsity. Even if you don't have the law of explosion in a paraconsistent logic, ending with falsity is a sign to write a little, or to build a little fence around that area and say, while we don't know what's happening around here, near this area is something false, and we should stop working in that area because it will lead to inconsistent answers. So the elimination rule for not is to take not P and P and turn it into falsity. There's a nice abbreviation of this. We simply say not P and P entails false. This one's worth memorizing, but truth is, you should practice some of these yourself. Reread this a few times. Watch this part of the video until you get the nuance of the calculus here. We're always moving from premise to conclusion. Where it gets difficult is that sometimes we have a mixture of premises. Notice that this here is a premise to this conclusion over here. But then that whole thing is a premise to the larger conclusion. Let me make this very clear. Here's our first premise, and here's our first conclusion. Once we know this, we're simply making a statement about this premise becoming that conclusion. But then that whole thing is wrapped up as one individual premise, which will give us this individual conclusion. It's a layering of the logic. And I'll include a shout out to Attic Philosophy, which has an amazing video on the difficulties of reading sequent calculus and noticing what the nuances are about the different premises stacked together in this way. It's really important to sort out these differences. So here's our summary.